Next, we will introduce DC-DC converter, which includes boost converter, buck converter, and boost and buck converter. We only introduce buck converter in the first order circuit. Our natural thought of reducing the voltage is dividing voltage with resistors. But resistors consume power, and thus the efficiency of this type is too low. If the resistor isn't allowed to conduct all the time, can we connect the source to the load with a switch, which is turned on and off continuously? The voltage of load is a DC like this. Its average voltage is lower, but similar to the previous example, the load voltage also has large fluctuation, which is not satisfying. The previous smoothing capacitor realized a function of keeping the voltage in a short time. Can we take advantage of the inductor to keep the current in a short time with such a circuit? If the circuit has large value, which keeps the current flows through RL when the switch is open, then the load voltage is kept constant. Is this design practical? No, it's not practical. Don't forget the conclusion in lecture 48 that we cannot cut off inductor's current from the circuit freely. Do you still remember how to solve the problem in lecture 48? Yes, we use a flywheel diode. This is a basic circuit of the buck chopper. Next, let's analyze the buck chopper. The difference from the previous circuit is a MOSFET is substituted for the switch. MOSFET is a common switch element in the power electronic circuits. Before analyzing, let's run a simulation first. The simulation circuit has the same topology as the circuit analysis. The elements are voltage source, MOSFET, inductor, resistor, and diode. We need to point out that if MOSFET is turned on and off, alternatively, a sequence wave signal should be exerted between G and S of MOSFET. So one terminal of the square wave signal is connected to G and another is connected to S. The positive terminal of channel A is connected to G of MOSFET, and the negative terminal is connected to S of the MOSFET, which means that channel A observes the driven signal of the MOSFET. The positive terminal of channel B is connected to the load and the negative terminal is connected to the ground. The two-channel oscilloscope in multisim is isolated, so it can display the driven signal of the MOSFET and the voltage signal of the load simultaneously. Now we run the simulation. You can see that red line represents the driven signal of the MOSFET. The green line represents the voltage signal of the load. The scale of the channel B is 5 volts per dive. So the average voltage of the load is more than 5 volt. It's relatively smooth. The input DC voltage is 12 volts. It's reduced. So the circuit realizes the function of buck chopper. From the simulation, we can see that the load voltage is a relatively smooth DC and its value is lower than the source. Now we focus on the key waveforms in the simulation. We get the voltage of the load in the simulation, and here we draw the current of the load here. But because the load is a resistor, so the ratio of the voltage and the current is a constant coefficient. The black line represents the current of the load. The red line represents the control signal between G and S of MOSFET. When the red line is at high level, the whole switch is turned on. When the red line is at low level, the whole switch is turned off. So naturally, the circuit can be divided into two parts. We analyze them respectively. The equivalent circuit of the first part is like this. In this time period, the switch is turned on, and the diode withstands reverse voltage, so the diode is open. We don't draw it here. This is the first order RL circuit. We can use three elements method to analyze it. From the figure, we know that I0 plus equals I1. So what's the steady state value of I? Is it I2? No. We've discussed this question in lecture 50. When the circuit is switched at t equals 0, we don't know it will be switched at t equals t on. So its steady state value should be US over R after switching at t equals 0. Tau equals L over R, so we can get that I equals US over R plus I1 minus US over R times e to the power minus t over tau. This is the analysis of the circuit in the time period from 0 to t on. The second time period is from t on to capital T, or from t on to t on plus t off. Now between GNS of MOSFET there is low level, so it's open here. The diode conducts, and this is the equivalent circuit. Suppose the diode is ideal, so here's no resistor here. This is still a first order RL circuit. We can use three elements method to analyze it. IT on plus equals I2. I infinite equals 0, and tau equals L over R. Then we get that I equals I2 times e to the power minus t on over tau. The two equations have an undetermined coefficient I1 and I2 respectively. According to the analysis in lecture 50 and 52, the key factor of solving the equation is their steady state values. For this circuit, when t equals t on, I equals I2. For this circuit, when t equals t on plus t off, I equals I1. By solving the equations, we can get the value of I1 and I2. The analysis of the whole circuit is then finished.